So we're going to go through a kind of standard multivariable calculus question here. The question looks like this. Integral 0 to 2, and then integral 3y to 6. We're going to integrate e to the x squared, and then with respect to x, and then with respect to y. So dx dy. Now, the standard technique here is to change the order of integration. The reason you need to do that is that if you try and integrate e to the x squared with respect to x, there's just no nice antiderivative here. So we switch the order, and you integrate e to the x squared with respect to y, well, you get y times e to the x squared, and then hopefully something nice happens. So that's almost certainly what somebody who gives you this question is expecting you to do. So the point of this video here is going to be to show you what you can do to do this in a totally different way, where you don't really have to switch the order of integration. We're going to start off with sort of the standard approach, switching the order of integration here. So to do that, the first thing I'm going to do is draw my region. So I'm going to draw my xy axes, and I'm going to do the y bounds first. Y goes from 0 to 2. So there's 0, or 1, 2. So here's y equals 0. This function here, so it's y equals 0. And then we have a function y equals 2. We know our region is between these two red lines. And then our x bounds go from 3y to 6. So 6 is probably simpler to draw. Here's 6. So let's maybe draw a bound of the 6 here. And then we have x equals 3y. So let's look at this. This point here, intersection, we have y is 2, x is 6. That's 6, 2. So x, if I look at x equals 3y, let's see, 6 equals 3 times 2. That is a point on the line. The origin is another point on the line. And so that line, include those 2 points. That's x equals 3y. Missed the origin a bit there. So the region we're trying to integrate, we're going from 3y out to 6 in the x direction. So sort of a rectangle would look like this. I'll draw it as sort of a double-ended arrow. And so the region we're trying to integrate is this triangle down here. Okay, so if you switch the order of integration, what you get is you get a double integral. You get still e to the x squared, but now we'll do this dy dx. So now I'm thinking x goes from 0 to 6, and then y is going to go from, well, this bottom function is 0, so I get sort of a, let's maybe draw this in green, get a vertical sort of cross-section like this. We go from y equals 0 up to the function y equals, we have to solve x equals 3y for y. So that's y equals x over 3. So y goes from 0 up to, whoops, not y over 3, but x over 3. So there's our integral. Not so bad. Let's go evaluate this. So what we get, I get an integral from 0 to 6. When I integrate e to the x squared with respect to y, I get e to the x squared times y. E to the x squared is a constant as far as y is concerned. And then we evaluate this at y equals 0. We subtract that off from what happens when we evaluate this at y equals x over 3. Okay, so now what we get 0 to 6. When you plug in x over 3, you're going to get x over 3 e to the x squared. I guess I wrote it in front, the y in front here. We plug in y equals 0, that's going to be 0. I'm going to subtract that. I don't really need to write that. So now we're here. Now what's different from our original integral, effectively, is that we have this x here. So what that's going to allow us to do is a u substitution. So I'm going to let u equal x squared, and then du is 2x, dx. Here. So I already have the x here, so I need the 2. And so I'm going to just kind of rewrite this as, we're going to write it as integral from 0 to 6. I want to write it as 2x e to the x squared dx. I have a 1/3. Also, I added the 2, so I have to pick up another 2. So I'll get a 1/6 out in front. So I'm going to get 1/6. And then the integral of 2x e to the x squared dx, that's just going to be an integral of e to the u, which is just e to the u. So what I'll get is e to the x squared. I'm going to evaluate that from x equals 0 to x equals 6. Get 1/6. E to the 6 squared is 36, minus e to the 0 is 1, and there's our answer here. So that's likely sort of how someone who gave you this problem was expecting you to go about things. Let's do this in, now, completely different method. It's being power series. So what we're going to do, our double integral. It was 0 to 2. I'm going to go up and make sure I remember what it was up here. 0 to 2, and then 3y to 6. And we had e to the x squared dx dy. Okay, so now you want to say, I don't want to mess around with that geometry of changing the order of integration. I'm going to do this a different way. To do that, what I'm going to do is I'm going to do an integral from 0 to 2, and then an integral 3y to 6. I'm going to replace e to the x squared with its power series. So I need to remember this, so maybe recall here, or learn, perhaps, I don't know. E to the x, so the power series for e to the x was the summation n equals 0 to infinity. It's x to the n over n factorial. So this has an infinity in it on the right. There's some sort of statement of convergence. This will converge for every single x. Here. So this will converge for every single x. So e to the x squared then, well, I'm going to put an x squared where I see an x. So that's summation n equals 0 to infinity. X squared to the n over n factorial. But x squared to the n is just x to the 2n. So what I get is a summation n equals 0 to infinity. X to the 2n over n factorial. I can do this dx dy. Okay, now we have an integral of a sum. We can pull that sum outside here. There's some convergence issues. They're not really going to come into play for this question. Essentially, we're going to get everything converges sort of for every value of x as we go along. So e to the x is really nice. So what we'll get now, we're going to pull this summation. We can actually pull it out of the inner integral and out of the outer integral. So we get a summation n equals 0 to infinity. The n factorial on the bottom, I can pull out of both integrals as well because it doesn't have an x or a y. It's just a constant. So I get now an integral 0 to 2, integral 3y to 6, get x to the 2n dx dy. Now the thing is this x to the 2n we can integrate. So in some sense, this is one of the key ideas behind power series, is we can take an ugly function like e to the x squared, ugly being we don't know how to integrate it, and replace it with a polynomial, effectively, a sum of x to the certain powers, x to the 2n's here, turns out. And then we know how to integrate those. So that's sort of the general, one of the general reasons to work with power series. You could approximate this as well. And we're going to go through and we get n equals 0 to infinity. 1 over n factorial. Then we get an integral from 0 to 2. When I integrate x to the 2n, I get x to the 2n plus 1 over 2n plus 1. I evaluate that at the bottom at x equals 3n. I start at x equals 6. Then I'll have to integrate with respect to y a bit later on. And so what I get is n equals 0 to infinity. I can pull that 2n plus 1 out of the integral. Just like to get rid of those constants when I can, or collect them all together anyway. Integral 0 to 2. When I plug in x equals 6, I get 6 to the 2n plus 1. Don't need to write that so high because I got rid of the denominator. 6 to the 2n plus 1. And then I plug in 3y. So I get 3y to the 2n plus 1. And then it's a dy integral. Okay. We're going to continue on here. So I get my summation n equals 0 to infinity. 1 over n factorial 2n plus 1. I get an integral from 0 to 2. Oh, sorry, here I closed my bracket. I should have opened that bracket. Yeah. And we go 0 to 2. I'm going to get an integral 6 to the 2n plus 1. Whoops. And then this 3y to the 2n plus 1, I can split up as 3 to the 2n plus 1 times y to the 2n plus 1, just a rule of exponents, dy. And that's just going to allow me to integrate this with the power rule. And so what I get is n equals 0 to infinity, 1 over n factorial 2n plus 1. Let's see, 6 to the 2n plus y. When you integrate with respect to y, you get 6 to the 2n plus 1 times y. So it's 6 to the 2n plus 1 in respect to y. 6 to the 2n plus 1 times y. Minus, I have a 3 to the 2n plus 1. And then I add 1 to my exponent, so I get y to the 2n plus 2 over 2n plus 2. So I get that, and I should evaluate from y equals 0 up to y equals 2. And now we've gotten rid of the integrals, at least. Well, we got to evaluate at y equals 2 and y equals 0. we get n equals 0 to infinity, 1 over n factorial times 2n plus 1. Let's write that a little nicer. And what I get now when I plug a 2 in for y, I get 6 to the 2n plus 1 times 2. I'm going to write that times 2 in front. And minus 3 to the 2n plus 1 times 2 to the 2n plus 2. I'm plugging in a 2 for y, all over 2n plus 2. And then when I plug in y equals 0, both terms are actually going to be 0. So subtraction does not matter. Okay, now we need to simplify this down. We'd like to get an answer that doesn't have the series in it. So what we get, n equals, or summation n equals 0 to infinity. What I'm going to do, 2n plus 1, I'm going to multiply through by 2n plus 2 to cancel out this denominator. So I'm going to get a 2n plus 2 in the denominator. And then I'm going to multiply through by a 2n plus 2 within the fraction. I'm going to get a, or within the parentheses, I'm going to get a 2 times 2n plus 2 times 6 to the 2n plus 1. And then the 2n plus 2 will cancel in the second term. So I'll get a 3 times 2n plus 1 times 2 to the 2n plus 2. So all I did is I multiplied really through by 2n plus 2, both terms here. That was basically to get rid of this denominator. I kind of factored out a 1 over 2n plus 2 would be another way to look at that. So let's do the next step here. We have 1 over n factorial, 2n plus 1, 2n plus 2. And then what we get inside here, let's see, we have 4n plus 4 times 6 to the 2n plus 1 minus, well, I'm going to rewrite this as second term as 3 to the 2n plus 1 times 2 to the 2n plus 1, and then I have another 2 left over. So I had 2n plus 2 2's, pull off 2n plus 1 of them, there's another 2 left over. It'll finish here eventually. I get 1 over n factorial, 2n plus 1, 2n plus 2. And now what I can do, I have my 4n plus 4 to the 6 to the 2n plus 1. I'm going to leave that. It's a rule of exponents. When I have the same exponent, I can multiply the bases. So this is 6 times to the 2n plus 1, and then I have the times 2. And what that's going to allow me to do is factor out this 6 2n plus 1 from both of the terms. So I'll get a 6 to the 2n plus 1 over n factorial times 2n plus 1, 2n plus 2. And what I'm left with is 4n plus 4 from the first term minus 2, the coefficient of 6 to the 2n plus 1 in the second term. Okay, but that is, let's see, I'm just going to do 6 to the 2n plus 1 for n factorial, 2n plus 1, 2n plus 2. This 4n plus 4 minus 2, that's 4n plus 2. Okay, so now things are going to start getting a lot nicer here real quick. I'm going to do n equals 0 to infinity. 6 to the 2n plus 1. I can factor a 2 out of the 4n plus 2. So that's 2 times 2n plus 1. On the bottom, I have an n factorial. I have a 2n plus 1. That's going to eventually cancel. The 2n plus 2, I can factor a 2 out as well. So I get 2 times n plus 1. And then I get some nice cancelizations. The 2n plus 1s cancel, and these 2's cancel. So what I'm left with is 6 to the 2n plus 1 over n factorial times n plus 1. Now there's a nice way to write n factorial times n plus 1. Remember, n factorial is 1 times 2 times 3 times 4 up to n. Well, if I really have the next factor that'd be missing in n plus 1 factorial. So what I get is a summation n equals 0 to infinity, 6 to the 2n plus 1 over n plus 1 factorial. So I've combined n factorial and n plus 1 to be n plus 1 factorial. All right, now what I want to do is write this in a closed form. I'm going to use my power series to do that. So one thing I'm looking for here, I'm trying to remember the series, and that's n equals 0 to infinity, x to the n over n factorial. This was the e to the x. That's what we used earlier. So I want something that looks like this here. Well, I've got an n plus 1 factorial on the bottom. I'd like to get an n plus 1 factorial on the top. Or not n plus 1 factorial, exponent of n plus 1 on the top. So to work toward that, first thing I'm going to do is I'm going to pull out a 6. So I can rewrite this 6 to the 2n plus 1 as 6 to the 1 times 6 to the 2n. And I have an n plus 1 factorial on the bottom. And then what I'm going to get is, let's see, summation n equals 0 to infinity. I can pull the 6 out in front of the summation. It doesn't have any n's in it. And then 6 to the 2n plus 1, I'm going to write as 6 squared to the n. Just a rule of exponents says I can do that. If you had 6 squared to the n, you'd multiply n times 2. It would be 2n. And then I get 6 summation n equals 0 to infinity. This gives me, let's see, 36 to the n over n plus 1 factorial. I'm getting closer, but I want the n plus 1 and the n to match. So what I can do to make that happen is I can multiply the top and bottom by 36. And when I do that, I'm going to take the bottom by 36 outside, and on the inside I multiply by 36 on top. That's going to give me a 36 to the n plus 1. And so now these at least match, which is good. One quick simplification, 6 over 36, this is 1/6. And again, the n plus 1's match, but I really want those to be n's. So what I'm going to do, I'm going to sort of re-index here. Instead of n equals 0, let's make a substitution, really, and let's let n plus 1 equal k. Well, then, let's think about what happens to our series. Or not n equals, now we're going to switch to k's. K equals, well, when n is 0, 0 plus 1 is 1, k is 1. When n is infinity, well, infinity plus 1 is really still infinity, so I get an infinity. And then I'm going to get a 36 to the k over k factorial. A lot of times people rewrite this using n, so you'll see people write this as 1/6 summation n equals 1 to infinity, 36 to the n over n factorial. The general rule I'm going to think of is I'm going to add 1 in my indexing situation, and then I subtract 1 from n sort of within the thing I'm summing up. So the n plus 1's become n's. I want to subtract 1. It means I add 1 to each of the bounds of my summation. That's just doing a substitution, n plus 1 equals k. Okay, almost there. We've got another problem with our e to the x series. So if you look at this, we have an n and an n, but we're starting at 1. E to the x, I need to have a 0 down there. So we can force that to happen by saying that this is 1/6 times, well, if I did a summation n equals 0 to infinity, let's do it another way. Let's do n equals 1 to infinity, 36 to the n over n factorial. What I want, really, is the n equals 0 term here. So I want to add, let's just go off to the side here, 36 to the 0 over 0 factorial. 36 to the 0 is 1. 0 factorial is also 1, so that term I'm missing is a 1. So I want to add a 1. If you did that, you could do a summation n equals 0 to infinity. You could use the formula for e to the x. But I can't just add 1. I have to subtract 1 as well. And so what I get then is 1/6 summation n equals 0 to infinity. I get a 36 to the n over n factorial. So that's adding these first two things together, the series with the 1, and then I subtract the 1. And now, basically there, this series, this is like e to the x, but the x is replaced with 36, so that's e to the 36 minus 1. And we get our answer that way. And we'll go back and look, and that'll match what we did with the changing the order of integration quite a while ago. Here, way up here, 1/6 e to the 36th minus 1. Way down here, 1/6 e to the 36th minus 1. So both ways give us the same answer, which is good. Probably you really want to do the changing order of integration method. The power series, I just want to show you this works. You can kind of get away this, impress your friends or instructor or whatever here. You could probably shortcut this power series method a bit if, maybe I'm showing more steps than I need to. The other point here is sometimes that change of order of integration thing doesn't work, but this power series thing for e to the x squared should basically always work here. As long as I get sort of polynomial bounds, I can do that. So sort of a more general method gives you a little more power here to do things.